Okay, thanks. Okay, so I will start today with a small discussion on canonical heights. So maybe Antoine already did it, but maybe not too bad to do it again. So that's in a sense, that the end of lecture 1. So canonical heights. So again, I'm not an expert in number theory, so I apologize if I say a few stupid things. So first, let me remind a few things about the naive height on P1 of Q bar. So you know certainly better than me that if x is a rational number, say P1 over the rational number, you can define the height, the naive height, it's naive height of x as the max of, so you write x as in homogeneous coordinates as pq, where pq are rational numbers and are integers which are relatively prime, and it's the max of log p and log q. Perhaps you should put moduli here. Okay, and if x is different from infinity, then you can write it as x1, and then you get log plus of x. Of the is it correct? I think so. Okay, now if x is not a rational number but an algebraic number, is algebraic in some number field, then you can extend the definition of this naive height by so there are several ways of doing it, and one way which is useful in view of future dynamical applications is to decompose the height as a sum of local contributions. So the formula is something like this. So you look at all possible completions of Q. So you will introduce the set of prime numbers plus the place at infinity, and so let me just give you the formula because it's easier like this. So the formula is given by this. It's 1 over the degree of the extension times the sum over all places. So for each place P, maybe P is infinite, you have a number of you have a way of embedding C K into CP. So for P equals infinity, it's the classical complex plane. For P a prime number, it's CP in the sense you know it. And you have several ways of embedding your number field in CP, and you will sum over all these embeddings. So you look at all possible embeddings of K into CP, and you sum a contribution which is basically the same. So X is X naught, X1, and you take the log of the max of x naught and x1. And I think there should be a plus somewhere. Let me check. No. And here, the absolute value is the p-adic absolute value. Okay, so don't mind the exact form of the formula. So I think the formula here is correct. You can define the height of an algebraic number by summing local contributions. Okay, so now let me take a rational map. So let me take F, a rational map, which is defined over the algebraic numbers. So it's a rational map defined over Q. So it maps Q bar. It maps P1 over Q bar over itself to itself. Okay, and so it acts on this height. And there's a simple proposition or lemma proposition. And apparently this is due to Northcott. You can easily, so it is of degree D. And you can compare the height of the image with the height of X. And the proposition is like this. I have a doubt. Yes, there exists a constant C, which depends on F, such that the height of f of x minus d times the height of x, so it's always the naive height here, is bounded by C. So how do you prove this? So remember yesterday, I said that whatever field you look at, so either C or CP, you have an estimate of this form. So the proof, so I don't do the complete proof, but I give the main argument, is based on the estimate which I gave yesterday at the end of the lecture. The logarithm of f of xy, so let's, yes, f of xy over xy to the d is comprised between two positive constants. Okay? And here this works over C, but it works also over CP. Now you look at all these contributions. So, and of course for P large enough, so you will only see finitely many contributions. Okay? Because for P large enough, everything is equal to 1 here. So you will sum finitely many contributions where you have such an estimate. And if you look at the formula, it gives exactly this. Okay? So now, starting from this proposition, so there's a construction by, I think it's Cole and Silverman. So it's the construction of the canonical height, HF. So this is a very easy, a very easy fixed point argument. So there exists HF, so it's a height function, such that, so it is at bounded distance from the standard height. So HF minus H is less than some constant, depending on F. And also, it is invariant under F, in the sense that if you compose it with F, you get D times the height. So that's the so-called canonical height. And so it's not the same constant, right? The proof is easy. So you see, writing this is saying that you have a certain H is a fixed point under a certain operator, which is 1 over D, H, 1 over D composition with F. So you just, either you apply the fixed point theorem or you reprove it. And so actually you introduce Hn, which is 1 over D to the n H composed with Fn. And you have to prove that it converges. So if Hn converges to something, to some H infinity, then H infinity will be a solution. Then H infinity satisfies that H infinity composed with F is D times H infinity. Okay? And actually, why is the convergence true? And actually, the convergence holds. Just we do exactly what we did yesterday with the grain function. You just write this as the sum of a series. So Hn plus 1 minus Hn is 1 over D to the n plus 1 H composed with Fn plus 1 minus 1 over dn H composed with Fn. So it is 1 over dn h, so 1 over d, no, let's say 1 over d n plus 1, h composed with f minus dh composed with f to the n plus 1, to the n. Okay? And as I just wrote here, this is bounded, this term here is bounded by c. Okay, so this whole thing is bounded by c over d to the n plus 1. So this series of functions is a convergent series of functions, and the limit satisfies exactly what I want. Okay, and this estimate is easy because, well, it's also part of this convergence. Okay. So we have a height on P1 of Q bar, which is well adapted to the dynamics. Then it satisfies a number of interesting properties. So first, it's non-negative. It is non-negative. So we can characterize the points of height 0. So points of height 0 are exactly the points which are pre-periodic under the dynamics. Pre-periodic means that you start with x, you iterate it a number of times, and at the end, you get a cycle. So that's a pre-periodic. So h, so maybe it's already periodic, but maybe not. H of fk, so there exists two integers, one bigger than the other, such that fk of x is equal to fl of x. And last property, the set of point x with bounded degree and bounded height is finite, such that x in P1 Q bar with bounded degree and bounded degree and bounded height is finite. Okay, so where does this come from? So it's not difficult. So of course, maybe let me say something, remark. If I should have said it before, if you consider the mapping z goes to zd for some d, okay, what is the canonical height associated to this map is exactly the naive height. So let's the canonical height is exactly the naive height. I mean, it is clear from the construction. So in that case, this statement is exactly the classical Northcott theorem. Okay, so this the statement, the proposition, is the Northcott theorem. This boundedness here is the classical Northcott theorem, and the second point is the fact that points of height 0 are just roots of unity. So roots of unity are exactly the points in the plane which are pre-periodic under default power. So, and then the proof now of this proposition is exactly the same. Well, it's similar to Northcott theorem 2. So the proof. The first point is obvious from the construction because it is obvious from this construction. So Hn is non-negative by construction, and it converges to HF. So HF must be non-negative. The third point follows directly from the Northcott theorem. So it follows from the classical Northcott finiteness, since H, the canonical height, is at bounded distance from the naive height. So points of bounded canonical height are also of bounded height. Okay? And finally, for point 2, so there are two implications. So let's start with the reverse implication first. Assume that x is preperiodic, so fk of x is fl of x for k different from k bigger than L, and you just take heights. So h of this is d to the k h of x, and this one, height of fl of x, is d to the L h of x. This is equal. So you get that d to the k is equal to d to the L, unless, no, you get that dk h of x, dk minus dl h of x is equal to 0, but this is non-zero because k is different from L. So it implies that the height of x, so it's the canonical height, is equal to, so all this is canonical height. Canonical height must be equal to 0. Okay? For the direct implication, you start with a point of canonical height 0. So let x be of canonical height 0. And iterate it. Look at all the iterates of x. So sorry, the blackboard is really dirty. And then this implies that for every positive k, for every positive k, yes, the height, canonical height of fk of x is equal to 0. So it is uniformly bounded. Now, all these points, so you start with a point in P1 of q bar, and you iterate under a certain rational function. It will not raise the degree. It may raise the degree of the extension finitely many times, but the degree of these points, so the degree of this point is also bounded. Okay, so all these points, all the iterates of x, they live in a finite extension of q bar, and they have 0 height. So they must live in this finite set. Okay, and now if you, so that's a very simple idea. Perhaps if you've never seen it, you have to think a little bit. If you iterate a mapping in a finite set, then every point must be preperiodic. There must be a collision. So you have a finite set. It's just a pigeonhole, right? You have a certain finite set. You iterate the mapping. Start from every point. You start to iterate. At some point, you have to have a collision inside the orbit. Okay, all the iterates cannot be distinct. Okay, and then so you conclude by so let me be clearer here. So therefore, the whole orbit of x is contained in a finite set. So by pigeonhole principle, it implies that there exists some different integers such that fk of x is equal to fl of x. And that's the end of the proof. OK. So just a final comment on this canonical height section. So I defined, so I erased it, but I recall the definition of the canonical height. You start with the naive height, and you apply fixed point. You apply the fixed point theorem to get this canonical height. So it is useful to know, so that's a final remark. Actually, you can define the canonical height also by a sum of local contributions. So it is, so I will come back on this later. It is possible to define HF by a sum of local contributions. And actually, we have all the ingredients for that because we define the green function and non-Archimedean places. So it's the same formula. Let me just it in plain words. So it's the same formula as the naive height, except that you must replace the log by the green function which was defined yesterday, except that the logarithm is replaced by the green function at the corresponding place. Okay, I will come back on this later. Actually, not so far from here. Okay. So from this canonical height definition, we can apply. So again, we will discuss a little bit the equidistribution theorems for points of small height. So I will not be super precise on this. So Antoine will state and prove them precisely in his lectures. But let me already say that there are some. So we will see plenty of consequences of equidistributions of small points. But let me already state we have first consequences of equidistribution of small points. Distribution of small points. So I don't state the general equidistribution theorem, but let me state a consequence. So that's a corollary of, say, Nguyen theorem. So we will recover two results that were stated yesterday, the equidistribution of preimages and the equidistribution of periodic points. So let's go. Let f a rational function defined on Q bar. Let Zn be any sequence, any non-infinite sequence of pre-periodic points. And of f, and look at the measure which is equidistributed. So you take the measure which is equidistributed on the Galois orbit of Zn, Galois group here. You take Dirac masses at the Galois conjugate of Zn, and you divide by the degree. So you get a sequence of point masses in the sphere. This converges to the canonical measure μf in P1 of C. Actually, so, and let me say same property, so same result. If now Zn is a sequence of preimages, okay, is a preimage of Z for some fixed Z, for some Z in Q bar. Okay, so the reason for this is that in this case, these points have height 0. So this is a point of height 0. So we actually have a sequence of points with height tending to 0. And here in this case, the height converges to 0. The height is something like height of z over d to the n, which converges to 0. So in any case, in both cases, you have a sequence of points of small height. And using this equidistribution theorem, you get this equidistribution in C. Let me just make a small remark. I don't know if I will use it. Actually, this, as I said yesterday, it is quite easy to define the green function and over other completions of Q. What is more complicated is to do measure theory because it requires Berkovich spaces. So if you are able to define what a measure is in CP, okay, so I don't want to comment about this, but if you're able to do the measure theory over CP, then this kind of convergence also holds for finite places. So remark, so the convergence holds at finite places, at non-Archimedean places, say, provided, let me say it like this, provided measure theory makes sense. One is able to make sense of measure theory. Measure theory meaningful. And this requires Berkovich spaces. So the convergence is also correct at finite places, but you need to know what a measure is, which requires some technology which I don't want to develop here. OK. So let me move on to the second part of these lectures. So now part 2 is really starting. So part 2 is about parameter spaces. So parameter spaces questions. So the setting is something like this. If you take, so let me go back to complex numbers. If you take a family, of rational mapping, so take a holomorphic family of rational mapping, of rational mappings of degree d, so the degree is constant, and the parameter space is some complex manifold. So you can assume it's the unit disk. Okay? It is quite important in dynamical system to understand how the dynamics of F changes when you move the parameter. Okay, so the basic question. How does the dynamics of F lambda depend on lambda? And usually what we are able to do is to make a dichotomy of the parameter space. So usually this defines a dichotomy of the parameter space, which is slightly similar to the dichotomy of Fatou and Julia, into a stability locus and a bifurcation locus. So the stability locus is an open set where the dynamics is locally stable. Dynamics is locally stable. Whatever this means, I don't need to be very precise here. So the dynamics does not change too much here. And the bifurcation locus is the complement. So remember, it's quite similar to the Fatou-Julia dichotomy. Philosophically, it's similar, and actually there are some strong links between the two. I don't need to be too precise here. And as it turns out, when the family F lambda is defined, if now the family is defined over Q bar, so if the family is algebraic and defined over a number field, it turns out that arithmetic ideas can be used to understand a little bit this precisely the bifurcation locus. So I will discuss these questions mostly. So I will discuss these questions. So mostly for polynomials. But it is also very interesting for general rational maps. So let's start with the most classical setting. The most classical setting is the case of quadratic polynomials. So first case, the space of quadratic polynomials. So of course, a quadratic polynomial is of the form az squared plus bz plus c, where a, b, c are complex numbers, and a is non-zero. So now when you do dynamics, when two mappings are conjugate, they have the same dynamics. So if you conjugate by an affine map of the plane, so affine mappings depend on two coefficients, so you can kill two coefficients. Okay, so actually you can be more precise. By conjugating by homothecy, you can make A equals 1. And if you then conjugate by a translation, you can make B equals 0. So what remains at the end? It remains only one parameter. So finally, the space, so the space of quadratic polynomials modulo affine conjugacy is actually almost, so it's almost true, I will say why, to the family of polynomials z squared plus c for c in C. So what I say is that every conjugacy class has a representative of the form z squared plus c. And actually, this representative is unique, except for c equals 0 when you have an additional symmetry. Okay, for c equals 0, the mapping z squared has an additional symmetry, which is just z goes to minus z. So this bijection here is true, except for c equals 0. But you don't care about this. OK, so let me discuss the dynamics of this quadratic polynomial. So remember the definitions of yesterday. Yesterday I defined, for a mapping F, I defined K is the filled-in Julia set. Which is the set of points with bounded orbit. Set of points Z such that, so I will usually denote it by P sub C. PCN of Z is bounded in the plane. And the Julia set is actually the boundary of K. Okay, and if you are not in K, you go to infinity. Okay, so let's go. So fact. So a very easy computation. If the modulus of Z is bigger than, I think it's square root of C plus 2 plus 1, then, so that's a very easy exercise, Z squared plus C the modulus is bigger than 2 modulus of z plus 1. That's a very trivial exercise. I don't know if it's optimal, but at least it's correct here. So it implies, by iteration, of course, this goes to infinity because you multiply the modulus by 2 at each step. Okay, so it implies that the iterate goes to infinity. Goes to infinity. Okay, so it means, so a consequence of this is that the field Julia set of the polynomial PC is contained in the disk of a radius square root of c plus 2 plus 1. Okay, so you have a, depending on C, you have a big disk, and all the points outside go to infinity. Actually, they go to infinity at super exponential speed because they go to infinity like z to the 2 to the n. Okay, what happens inside now? So if you fix this radius r, if you want to understand what the Julia set looks like, you have to pull back. So by definition, by just what I've just said, if you take the pullback of this disk of radius r, you get something which is relatively compact in the disk. Okay, so when you pull back, you get something which is smaller. So what is it? What is this set? What is this set? So it is defined by something like it is the set of points in the disk of radius r such that P is smaller than something. Okay? So by the so when you have a region like this, the set of points where a polynomial is smaller than something, so it is something bounded by a certain Dujardin curve, and by the maximum principle, it is a union of disks. Okay, it cannot be an annulus, for instance, because such a region, if a polynomial P is smaller than R on this region, by the maximal principle, it is also smaller than 1 inside. Okay, so this is a union of topological disks. This is a union of topological disks. And actually, there are two possibilities. There are two possibilities. So I want to describe the topology of this set. And basically, there are two cases. You can apply the Riemann-Hurwitz formula. So by the Riemann-Hurwitz formula, the Euler characteristic of the preimage of the image, sorry, is 2 times the Euler characteristic of the preimage. Oh, sorry, I'm lost here. No. Sorry, I'm lost in my formula. Let me check on my notes. Okay, let me do it. Sorry. Yes, it's a preimage of the image minus the ramification term. Okay? So here, the Euler characteristic of a disk is 1. Euler characteristic of the disk is 1. And you have at most 1 ramification point. So I should have said it. The critical, so there is only one single critical point, which is 0. So the critical set of PC is just the point 0. So you have, you have two possibilities. Either the ramification term is equal to 0, and then the Euler characteristic, well, the preimage of the disk is the union of 2 disks. I will make a picture. Either the ramification term is 1, and the preimage is 1 disk. So the picture is like that. You have two possibilities. So you have case 1. So what does it mean that the ramification term is equal to 0? It means that there is a critical point at 0. It means that it is mapped outside this disk. So that's the disk of radius r. And that's P of 0. If it is mapped outside of the disk, then the preimage of the disk is the union of two disks, of topological disks, which are disjoint from 0. If, so that's case 1. And case 2, if 0 is mapped inside the disk, then the preimage of the disk is only one disk which contains 0 and may or may not contain this point here. So you have something like that. So that's the preimage. So these are the two properties. And of course, you can iterate this picture. So when you iterate this, what happens? So when you iterate this picture, so you start by, you take the iterated preimage of this disk of radius r, and you get a sequence of nested sets. And there are two possibilities. And wait until 0 does not belong to this iterated preimage. And there are two cases. There are two cases. Case 1, you wait and it never happens. It never happens. It means that at every stage, when you pull back the disk, you get one single topological disk. So it implies that for every n, this preimage is actually a single topological disk. So in that case, so you will get that the intersection of all these guys is the filled-in Julia set. So it would imply, so it implies that the filled-in Julia set, which is the intersection over every n of these sets here. So a point, let me be clearer here. If a point does not escape to infinity, it means that it does not escape this large disk, right? Because if a point is outside the disk, I have proven that it goes to infinity. So not escaping to infinity means not escaping this disk. So the set of points which remain in the disk under all iterates is exactly the filled-in Julia set. So in this case, it is a nested intersection of connected topological disks. In this case, it is connected, because it is a decreasing intersections of connected closed sets. And in the other case, it happens for some n naught. It happens at some n0. So you can always assume that n0 is equal to 1. So the picture is still here. So assume now this is the first time it goes outside. What happens when you pull back? When you pull back more? Well, this disk here does not contain the critical value. So when you pull it back, you get, when you pull back this picture, this disk here, let me be, I'm going too fast. What? If the pullback looks like this, it means that you have two branches which both, so you have two branches of P which both map a small disk into a bigger disk. So now if I take the pullback of the big picture, the pullback of this disk under P has one component here and one component there. And the same for the other component. When you pull back this component here, you get one component here, one component there. And you can iterate this process And what remains at the end is a Cantor set, which is the intersection of all these components. So in this case, the field Julia set is a Cantor set. Just one small remark. It might happen that when I say that K is a Cantor set, I mean that these sequences of components shrink to point. A priori, it might be that you have a sequence of components shrinking to some non-trivial compact set. But as I said yesterday, non-critical holomorphic mappings are contractions for the Poincaré metric. So in such a situation, there is a certain metric which is automatically contracted by the preimages. So it means that the components really shrink to point. So here you use a contraction for the Poincaré metric. It is a very useful fact that holomorphic mappings, non-critical holomorphic maps, always contract something, contract a metric. Okay, so at the end, what we have proved the following theorem, which is the basic dichotomy for quadratic polynomials. Quadratic polynomials. Then let PC is z squared plus c. Then either k of PC is connected. And this is equivalent actually to say that the critical point 0 does not escape under iteration. So it is equivalent to the fact that 0 has bounded orbit. Or the Julia set, the field Julia set, which is equal to the Julia set in this case, is a Cantor set. And it is equivalent to the fact that 0 has unbounded orbit. Unbounded, and actually unbounded implies it goes to infinity. Okay, so you can ask a computer to make a map of a parameter space. And so you can introduce the set M, so-called the Mandelbrot set, which is a set of parameters C such that 0 has bounded orbit under PC. Okay, so you can ask a computer to draw it, and you see a picture like this. So you have a big component which is a cardioid. So 0, the parameter 0 corresponds to the map z goes to z squared. So in that case, the critical point is fixed. So certainly, it does not go to infinity. So 0 is inside the Mandelbrot set, and actually, it is inside a component which looks like a cardioid. And you have several components. So the picture is something like that. I think you've all seen it before. So here, there's a tip at the point -2. Here is 0. Here there is 1/4. And you have a bunch of components which basically look like the Mandelbrot set everywhere. Something like that. It is symmetric with respect to the x-axis, and you have a bunch of components converging everywhere. Okay, so you see a picture like that. So the Mandelbrot set is the interior of the picture, okay? And the outside, the interior of this full set here, and the outside is the outside of the Mandelbrot set. Okay, so let me already say that, so you have plenty of components. So actually the Mandelbrot set, M, you can write it as the interior of the Mandelbrot set together with its boundary, right? So when you are inside the Mandelbrot set, if you take a point in the interior here of the Mandelbrot set, it means that when you move a little bit the dynamics, when you move a little bit the parameter, the point 0 does not escape never escapes in some neighborhood, okay? And it turns out that when you move slightly inside the component, the dynamics does not change much. So actually, this is a place contained in the stability locus. On the other hand, when you are on the boundary, it means that under a small perturbation, the Julia set will go from connected to counter set. So this is certainly contained in the bifurcation locus. Okay? And there is also another interesting remark. So in this picture, there are special points. There are special points. So a special way for the critical set to have bounded orbit is when the critical set is periodic, okay, or pre-periodic. So points, parameters C, such that the critical point 0 is pre-periodic. And when it is pre-periodic, there are two cases. Either it is periodic, which means that the nth iterate of 0 is equal to 0 for some n. So you have point 0, which is mapped under iteration to itself. Since 0 is a critical point, in that case, the multiplier, so it is a periodic point, right? And as I said yesterday, a periodic point has a multiplier. Since it is critical, the multiplier is equal to 0. So in this case, it is an attracting point. So 0 is an attracting periodic point. Okay, so these components, so the fact that 0 is an attracting periodic point, as I said yesterday, when you move a little bit the parameter, the attracting point persists. Perhaps it is not critical anymore, but it still attracts the critical point. So these points are inside the interior of the Mandelbrot set. So for instance, this is a point here, a point where 0 is pre-periodic. And actually, in every component, you have such a periodic parameter. So-called post-critically finite parameter. So the critical point has finite orbit. So the case where the orbit is periodic, these are points inside of these components. And the other situation is when it is strictly pre-periodic. And in this case, it must fall on a repelling cycle. So in this case, it is in the Julia set. So you have to admit this. 0 belongs to the Julia set in this case. And actually, these parameters C belong to the boundary of the Mandelbrot set. So for instance, so you have a, so let me put colors. So that's orange points and purple points. So the orange points are here. And the purple points are, they live on hairs of the Mandelbrot set. So the Mandelbrot set has components, it has hairs, it has very complicated structure. And these purple points, they actually live on the boundary, on hairs of the Mandelbrot set, everywhere. Actually, they are dense in the boundary. We'll see it in a moment. OK. So let me make a remark. Very easy observation. So proposition. A parameter C is in the boundary of the Mandelbrot set if and only if the family of mappings C maps to Fn Pnc of 0 is not a normal family about in a neighborhood, in any neighborhood of C. So it is a little bit like the definition of the Fatou set. You look at, so this is a sequence of holomorphic mappings which are depending on C. And you may ask whether this sequence is a normal family or not. And actually, this property of being a normal family, it characterizes the fact of being at the boundary of the Mandelbrot set or in the interior, in the exterior of the Mandelbrot set. So the proof is obvious if you think about it. So let me just say it in words. So what does it mean? If you are at the boundary of the Mandelbrot set, it means that the critical point has a bounded orbit, but there exists a certain small perturbation when it has an unbounded orbit. So certainly it is not compatible with being a normal family. So the implication here is trivial. And the opposite implication, if you are not a normal family, there are two cases. Either the point has bounded orbit or not. If the point has an unbounded orbit, actually it converges to infinity. And we saw that the property of going to infinity is an open property. So if the orbit is unbounded, the family is normal. Now, if the point has a bounded orbit, and it is not a normal family, it cannot be uniformly bounded due to the Montel theorem. So it means that it is bounded, but when you make a very small perturbation, it must be unbounded. So it says exactly that you are on the boundary of the Mandelbrot set. OK, so let me make a definition. So let's go back for a moment. So a new section, maybe. There's an aside here. There's a notion of active and passive critical points. So here I go back to the general setting of a holomorphic family of rational maps. And assume, so when you have a holomorphic family of rational maps, it is not always true that you can follow holomorphically the critical point. Because think about this one. If you try to find the critical point of these cubic polynomials, you do the derivative. It's 3z squared plus lambda. So the critical points are defined. They satisfy the equation z squared equals minus lambda over 3. And as you know, when lambda is in the neighborhood of the origin, you cannot follow them holomorphically. Okay? But so in this case, you cannot follow them holomorphically. But also, if you make a branch cover, if you make a slight change of parameter space, you can call this lambda, you can call it u square, okay, or mu square maybe, which means that you are taking a twofold branch cover of parameter space, and this will become mu square, and this will become mu square. Then you can follow them holomorphically. So what I'm saying here is if you take any family of rational mappings, maybe you cannot follow the critical points, but up to taking a branch cover, you will be able to follow them. So you can assume that the critical points move holomorphically with the parameter. And otherwise, if it's not the case, you just take a branch cover and you get this property. OK, so let me look at one of these critical points. So let me take definition. Let me take such a holomorphic family, and I mark a critical point. So it's a holomorphic family of rational maps with a marked critical point. I give myself a critical point. And I say that C is passive at lambda naught if there exists some neighborhood of lambda naught such that the iteration of this critical point forms a normal family in N. So this sequence of function is normal in a neighborhood. So it means that when you start with lambda naught and move a little bit the parameter, the orbit of the critical point does not change. Basically, you see the same orbit. And let me say that it is active if not. Okay, so what I've just said here is that the boundary of the Mandelbrot set is exactly the set of points where 0, which is marked here, is active. So activity of the critical points is a way of detecting bifurcations in the family. Okay, so there is a very simple proposition. Let me state it here. Proposition. So in the same context, so I take a family of rational mapping with a marked critical point, and assume that C is active. Assume C is active at lambda naught. Then there exists a sequence of parameters lambda n, a non-trivial sequence of parameters converging to lambda naught, such that at the parameter lambda n, the critical point lambda n is preperiodic, and actually it is preperiodic to a repelling cycle. Meaning that it is iterated a few times, then it becomes periodic, and this cycle here is a repelling cycle. Okay, and there is a variant. So either you can assume that it is preperiodic to a repelling cycle, or also there is also another sequence of parameters such that actually the critical point is periodic. So it's not the same sequence, right? So as soon as you have a critical point which is active, you can perturb it. You can perturb the parameter very slightly in parameter space so that the critical point becomes periodic, or if you prefer, preperiodic. And the proof is not very complicated. So a consequence of this, I lost my eraser. So corollary of this, let me just it here. So corollary. Well, as the orange points are dense in the Mandelbrot set. And also the purple points. Okay, because each time you take any point in the boundary, sorry. Okay, sorry. Let me be. So the set of critically, let me say it like this, the set of post-critically finite parameters, when you take the closure, it contains the boundary of the Mandelbrot set. And actually, you can take either the orange points or the purple points. And the proof, well, as soon as you're able to do this, you take a point at the boundary, you take any open set containing this point, and you know that the critical point is active in this open set. So there must be an orange point or a green point, purple point inside. Okay. So now the proof of the proposition. Proof of the proposition. Let me just prove the first item, but it's the same, basically the same proof. But so let me prove the first item only. Well, it is just Montel's theorem. So, so look at f lambda naught. This rational map f lambda naught admits plenty of repelling points. So it admits a repelling cycle of length at least 3, because remember, it has only finitely many non-repelling points and infinitely many repelling points. So you fix one of them, so you fix it, And this cycle, it persists, such a cycle persists under perturbation. So this is just the implicit function theorem. Okay, because the derivative is not equal to 1. Okay, so you fix such a cycle. So fix such a cycle. And you choose 3 points in the cycle. And choose 3 points. A of lambda, B of lambda, C of lambda in it. And they must be distinct because it's a cycle of period n. They are disjoint. Are distinct. Okay, now by a Möbius transformation, you can always assume, so if you conjugate by a Möbius transformation, you can always assume that this is 0, 1, and infinity. Okay, now remember that I have a critical point C of lambda. C of lambda is active at lambda naught. So it means that the family of mappings Fn lambda of C lambda is not a normal family in any neighborhood of lambda naught. So by Montel theorem, it cannot avoid 3 points. So by Montel implies that there must be a collision between one of these 3 points here. There must be a collision with the set 0, 1, and infinity. Okay? And that's the end of the proof. Because these points, 0, 1, and infinity, they are periodic and repelling. So that's the end of step 1. And the second item is basically similar. Okay, so there wasn't much of arithmetic geometry here. So let us introduce a little bit of arithmetic geometry. So let me state a theorem. So in a nutshell, special points are equidistributed. And I will be more precise in a moment on what I mean by equidistributed and equidistributed to which measure. And actually, you can choose again either the orange or whatever. I will maybe let us be more precise here. So more precisely, if you take any sequence, so let Cn be any sequence, non-trivial, infinite sequence of post-critically finite parameters, meaning that at such a parameter, the point 0 has finite orbit, then 1 over the degree of, so what does it mean to be post-critically finite? It means that you satisfy a certain equation. So if you look at the polynomial z squared plus c, actually this is an equation with integer coefficients. Okay, so these points c are certainly algebraic. So you can make the usual equidistribution thing, Galois conjugate of Cn. This converges to a certain measure mu, which for the moment I will denote it by mu m, which is a probability measure, supported on m, and it is actually the potential equilibrium measure of m. So this is the potential theoretic equilibrium measure. Okay, so this theorem, so in this form, I don't know exactly who it should be attributed to. So it was certainly known before. If you consider the set of all post-critically finite points, it was, I think, first found by Levin. And it was rediscovered a number of times, including by myself. So a number of authors. And then the arithmetic version, I don't know. It is a trivial consequence of, let's say, Bilou theorem. I don't know exactly who it should be attributed to. Certainly, Favre and Rivera-Letellier have something to do with it. And maybe Baker, Rumley. I don't know exactly. OK, so let's try to prove this. So we have to introduce a height associated with the problem. And so we will start by working at the complex place. So remember the green function. So remember the green function of a polynomial PC is the limit of 1 over 2 to the n log plus of the modulus of PCn of z when n goes to infinity. So this is the green function of the polynomial PC, which is also the green function of the Julia set. So now define, so it satisfies G composed with PC is 2G. And it is a subharmonic, it is continuous, and it is the green function of the Julia set. So define the function Gm is the function C. You evaluate the green function at the point C. So it mixes both dynamical space and parameter space ingredients. So you see that, so actually this function is continuous. So it has to do with the reason why it's continuous is because this limit is locally uniform. It is continuous, it is subharmonic. Okay? And so the Mandelbrot set is exactly the set of points where, so remember that G is positive, G of Z is positive if and only if Z tends to infinity. So this is also valid for the critical points. So the Mandelbrot set is exactly the set of parameters C such that Gm of C is equal to 0. And also, this function is harmonic on the set of points where it is strictly positive. And so all this implies that Gm is actually the green function. Oh, I missed a property, sorry. Gm of C, so you can make an asymptotic development at infinity. It is log equivalent to log C plus 0 plus small o of 1 when C goes to infinity. Okay, so it means that the Mandelbrot set has capacity 1. So all this implies that Gm is the green function of M. And in particular, you can take the Laplacian of Gm. It is the equilibrium measure of M. So that would be the measure which is here. OK, so if you want to define a canonical height, you need to do the same at finite places. And so I will define an adelic Mandelbrot set. Okay, so for P a prime number, I want to study the dynamics of z squared plus c on Cp. And actually, so you can do exactly the same. And you can introduce the set MP. It is the set of such parameters C such that, so here C is in Q bar, C is in Q bar, such that the orbit of 0 is bounded in Cp. And in that case, so this is the Mandelbrot set at the place P, and there is a simple proposition which is due to Favre and Rivera-Letellier. Actually, MP is the closed unit ball. So first, MP is the closed unit ball. For every such P. And also, you can define a green, so you have the green function G, how I want to denote it, I don't know, G at the place GPC at the place P. It is the limit, so of Z, it is the limit as n goes to infinity of 1 over 2 to the n log plus of the p-adic norm of Z, PCn of ZP. Okay, so this limit exists, as I said yesterday. And actually, GPC at the place P of C is just the function log plus of C. Okay, just so this is not difficult. Let me prove it. The proof. Okay, assume that the norm is smaller than 1, is not greater than 1, then, well, you use the ultrametric triangle inequality. By the ultrametric triangle inequality, C squared plus C is also of norm less than 1. And by iterating, you get that PCn of C is bounded. Okay? And likewise, if you assume that the p-adic norm is bigger than 1, then again, by the ultrametric inequality, this is equal to C squared. Okay? And so by iterating, you get that PCn of C, I should have put 0 here, n plus 1, it is C to the 2 to the n. Okay, so now if you take, so it proves the first item, okay, when C is less than 1, it is bounded. When it is bigger than 1, it is unbounded. And also the second one, because if you take 1 over 2 to the n log of this, you go to log plus of C. Okay, so it proves the two items. So with this, you can define the height. So you can define the height. Okay, let's go. So you can define the height associated to the problem, HM. So it is defined for C, an algebraic number, and you sum the contributions of all the places. So it is 1 over the degree of C times the sum at all places of the sum over all embeddings of QC in CP of the green function at the place P associated to Mandelbrot set of the point C, of the sigma of C. Okay, so exactly as the usual height. And actually there's a fact. h of m. Oh, I should have said something here. Sorry. Okay, let's say it. H of c is equal to 0 if and only if the parameter c is post-critically finite. Okay, and the reason is this one. So the proof of this is that you can define h pc of z by the same formula here, 1 over the degree of z, sum over all places, sum over all embeddings of qz in C, of the green function now at pc at the place p of sigma of z. So if I replace c by z in the formula, I get a certain function. And if you look at this function, it satisfies exactly the assumptions of the canonical height. It satisfies h composed with pc is 2h, because it is true at every place. And also h minus the naive, so it is hpc. hpc minus the naive height is bounded because it is, again, there are only finitely many places that you have to look at. And on every such place, the distance to the logarithm is bounded. So actually, it is the canonical height. So it is the canonical height of PC. So as I said, you can express the canonical height as a sum of local contributions. And we saw that for the canonical height, the height is 0 of a point C. The height is 0 if and only if the point is preperiodic. So if you plug in C here, the height will be 0. So hm is just the canonical height of PC evaluated at C. So the height is 0 if and only if the point C is preperiodic, meaning that the parameter C is post-critically finite. Okay? And then you just have to apply the arithmetic equidistribution theorem. So I don't have the time to state it precisely. Then you apply arithmetic equidistribution. So there's a fact which we admit here. So this height hm satisfies the assumption of arithmetic equidistribution. So I don't want to say exactly what it means. Okay, so the consequence. So we get, well, this implies the theorem. This implies the, it is not there anymore. It implies the equidistribution of post-critically finite maps in the quadratic family. So this will be a consequence. So the fact that this height satisfies the assumption of equidistribution, I think that Pascal will explain it. At least it will be a consequence of Pascal's lecture, last one, apparently. OK, so I see that the time is almost over. Let me start. So that was for the quadratic family. And now I would like to discuss higher dimension families. So I would like to discuss higher degree polynomials. So I will start the discussion. I will finish it tomorrow. OK, maybe let me already say that the space of the greedy polynomials. So as you know, the greedy polynomial depends on d+1 coefficients. And when you mod out by affine conjugacy, then you can kill two coefficients. So this actually space, you can prove that it is isomorphic to C d-1. And again, you have to put quotation marks here because there are a few special parameters where you have some multiplicity. So it's isomorphic up to, so actually this is a singular variety because there are some polynomials which have non-trivial symmetry, and when you resolve these singularities, you get CD minus 1. Okay, and so for instance, you can parameterize them like this. One possibility is to parameterize like this, ZD plus 0 plus AD minus 1, AD minus 2, ZD minus 2 plus blah, 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 up to A naught. So that's one possibility of parameterizing these polynomials. So maybe it is not the most useful. So tomorrow I will give better parameterization, but that's a way of parameterizing polynomials up to conjugacy. And again, in this space of, so when you take such a polynomial, so if P is of degree D, it has D minus 1 critical points. And as I said several times, if you want, the dynamics of critical points, in a sense, determines all the dynamics of PC. So what you have to understand if you want to understand the dynamics of a polynomial is to understand the dynamics of the critical points. And actually, that's the space, that's the moduli space of polynomials of degree D. Okay? And there is also the moduli space of polynomials of degree D with marked critical points. So it's critically marked. So with marked critical points, meaning that you can follow all of them holomorphically. And actually, it is also isomorphic to CD minus 1. So it is a branch cover of the previous one, and it is also CD minus 1. Okay, so in the space of polynomials, you have special points. You have special points, and these points are exactly the set where all these critical points are finite orbit. So post-critically finite mappings. So it's a set of P such that all critical points are pre-periodic. Okay, and there are classical results in holomorphic dynamics which say that the whole space of polynomials is somehow organized around these special points, exactly as the Mandelbrot set has one arranged point by component and all that. So there is a similar picture in the space of polynomials. And so you can ask, you can translate the classical number theoretic questions about a distribution of special points in this setting. So the goal here, is to study the analog of a classical number theoretic questions about the distribution of special points. Okay, so one question I would like to discuss in particular is this one. So in particular, I would like to describe the, I could call this the dynamical André-Hort conjecture. So dynamical André-Hort problem is to understand when a subvariety contains a Zariski dense set of special points. When a subvariety, so let's say X contained in the space of polynomials of degree D, has a Zariski dense set of special points. Maybe I should say first that I will prove it tomorrow. These special points, actually, there are Zariski dense in the space of polynomials. Okay, so the whole set of special points is Zariski dense, And the André-Hort conjecture in this setting is to understand when a subvariety has a Zariski-dense subset of post-critically finite parameters, and understand whether this variety is special or not. And so tomorrow, I think I will, so sorry, I'm slower than expected, so I will not be able, I think, to start the Manin-Mumford discussion, but I will discuss this André-Hort problem in the space of polynomials. And I think I will stop here.